In today's video on ice ages, we're going to talk about how past climates have changed dramatically throughout Earth's history, and we'll use this understanding to help us understand the magnitude of the anthropogenic climate change we're experiencing now. So as many of us are familiar with this theme of ice ages, we all know that climates have changed dramatically throughout Earth's history. So how do we know that what we're experiencing now aren't just natural changes? Well, it is true that over millions of years, we have had major shifts in the average global temperature. So if we look at this graph today, we can see that if this part of the axis is today and we go back in millions of years, 100, 200, 300 million years, at these scales over 2.4 billion years, we've had major changes in average temperatures on the Earth. Going from something like 50 degrees average Fahrenheit to up to almost 75. So these are massive swings in temperature. But the key that you need to understand is the scale at which these changes occurred had to do with how the Earth's crust was broken up into tectonic plates and was moving around. It was not related to these finer scale changes in carbon dioxide that we're noticing now. And the changes we're noticing today are happening much more rapidly than over these long time scales, such that at these scales, life had the opportunity to evolve to match the particular climate in which those species were found. In finer time scales, about 100,000 years, I want to introduce to you the concept of the Milankovitch cycles. This scale is caused by relationships between the Earth and the Sun. So let's again look at this axis now. Here we're now dealing with smaller time scales in thousands of years. Here we are today, 50,000 years ago, 100,000 years ago. And you can see that on this axis, the y-axis, we have average global temperature. Again, these are climate patterns. And right now, we are in what's called an interglaciation period. We're in a warming period. But if we went back about 20,000 years ago, we would have been in the middle of an ice age. And we would have experienced a significant average temperature difference that would have elicited spreading ice sheets all across the planet, including Indiana. So 20,000 years ago, Indiana, the northern part of Indiana, was covered with glaciers down to about Indianapolis. Those glaciers carved our topography flat. That's part of the reason why northern Indiana is so flat. And as you get south of Indianapolis, you get these rolling forested hills. That's because that's the extent of the glaciers that went south. In fact, if you would predict the pattern to continue through time, you might guess correctly that we are, according to these Milankovitch cycles, we are headed towards what would have been another ice age. This pattern would have periodically repeated itself throughout time. So what explains these Milankovitch cycles? What are they? Well, there are three orbital patterns that Milankovitch studied that he used to explain why we have these periodic ice ages every 20, 30,000 years. And so we're going to explore each of these one at a time, and I'm going to introduce them to you on this slide, and then you're going to watch a short YouTube video with me. The first has to do with what we call eccentricity. That has to do with the shape of the Earth's orbit as it goes around the sun. Now, I want you to realize this is extremely exaggerated. Eccentricity is the roundness of the orbit. It is almost perfectly round all the time, but its roundness changes on the scale of about 100,000 to 400,000 years. So sometimes the Earth gets a little bit further from the sun on the scales of hundreds of thousands of years in its annual trip around the sun, and other times it's less dramatic. So this is an exaggerated version of this. Remember, this is not why we have seasons. We do not have seasons because of changes in the distance that the Earth is from the sun. So sometimes it's rounder, and sometimes it's a little bit more elongated, not as exaggerated here. Obliquity has to do with the tilt of the Earth's axis. And so we explored last class period that we know we have seasons because of the change in the day length across a particular region of the world, related to the tilt of the Earth's axis. So the Earth's axis changes its tilt by several degrees every 41,000 years. So sometimes it's more upright and sometimes it's more tilted. It's never straight upright, and I'll show you more details about that in a second. And the third thing is that as the Earth is rotating, it's actually wobbling like a top. The Earth, we know, is spinning on its axis, and it's also revolving around the sun. And as the Earth rotates, it's pointing to a slightly different place in our galaxy. We call that axial precession. So that has to do with where the Earth is tilted as it's revolving around the sun, because that wobble occurs every 23,000 years. So depending upon where the Earth is tilted, in the sense of where it is located in its orbit, might also influence how much heat the Earth is getting from the sun. So let's watch this short YouTube video introduces how these patterns affect the prevalence of ice across the planet.
For just $67, you can make as many videos as you want, and you never need to pick.
What could have caused an ice age to happen? The question remained a mystery until around the First World War. A Yugoslav scientist named Milutin Milankovitch developed a theory. At the time, several mathematical models had been developed to explain subtle but significant variations in the Earth's orbit around the sun. Astronomers had calculated that the distance between the two and the shape of the Earth's orbit gradually changes every 100,000 years. And every 40,000 years or so, the angle of the Earth's axis tilts slightly. This affects where the sun's energy reaches the Earth. Using these and other measurements, Milankovitch calculated, with great mathematical precision, how the orbital variations had caused major climate changes over the history of the Earth. The changes began when a subtle shift in the Earth's orbit produced cooler summers and colder winters. This change created a domino effect that, year after year, century after century, allowed the glaciers to expand and ice sheets to grow. When the orbit of the Earth eventually changed again, the ice retreated. Milankovitch had discovered a mechanism to explain the creation of periodic ice ages. Today, most of Milankovitch's theory has been confirmed and accepted. It's estimated that the Earth may have experienced as many as 17 ice ages over the last several million years, with giant ice sheets covering as much as a third of the planet.
So how does this help us understand these ice ages? Let's continue in our work with that. So this diagram shows all three of those orbital processes in one diagram. The E stands for the ellipticity, so this is whether it's an oblong orbit or whether it's perfectly round or almost perfectly round. That slightly changes the distance. And then of course we have the precession. That is where the spinning of the top that we call the Earth is wobbling a little bit, therefore its axis is pointing to a slightly different place. And because that pattern changes depending on where it is in the orbit, that influences the amount of seasonality that the Earth experiences. And lastly, how much tilt we have in the Earth's orbit. We already know that would have a dramatic influence on seasons. So when you put these three things together, precession, obliquity, and eccentricity, they're all occurring at different time scales. We have time on this axis from now till the past. And when you overlay all those together, it changes the amount of total energy, that radiative forcing that the Earth is receiving, and therefore changes the climate. And that matches very, very nicely these stages of glaciation. So Milankovitch was mathematically able to predict these periodic periods of ice ages and warming periods, and ice ages and warming periods. So let's go through each of these one at a time. Eccentricity first. Again, eccentricity is how oblong the orbit is. Let's move this over a little bit. How oblong the orbit is around the sun. And it changes from a perfect circle would be 0. So 0.000055 is almost perfectly circular, to something pretty close to perfectly circular, 0.0679. You and I, using our naked eye, would not likely be able to tell the difference between the changes in the eccentricity. It cycles every 100,000 to 400,000 years. Our present eccentricity is 0.017, so we're kind of more close to the oblong side than we are to the perfectly circular side. And from the most extremes, you get a difference in heating of only about 6%. All right. So when you're closer to the sun, of course, that part of the world, the part of the year that you're closest to the sun, all parts of the world get approximately 6.5% more energy. That is not sufficient enough to explain the dramatic seasons we get. As we said before, that is due to the tilt of the Earth's axis. We are now closest presently around January 3rd. And so again, this would argue against the distance to the sun being the explanation for seasons, because we're experiencing winter when we're actually closest to the sun at this point. If we were closest to the sun when we were the most eccentric, that would mean we'd get 23% more heating than when further away. So this amount of heating change does vary depending upon the eccentricity of the Earth's orbit. That helps explain why we enter and leave these glaciation periods and interglaciation periods. Now let's talk about the changes in the tilt of the axis. The average is about 23 degrees. It ranges from 22 to 24.5, and that cycles every 41,000 years. So currently we're about 23.44 degrees, and we're kind of halfway between the extremes. So we're not at either extreme in our current time period. And we're in a decreasing phase of its cycle. We'll reach its minimum value closer to 22 degrees, around 11,800. The last maximum was reached 8700 before Christ. All right, so we're going from by decreasing, I mean we're getting more and more upright. So what does this cause? This trend by itself tends to make winters warmer and summers colder when we get tilted straight up. So in other words, as you would predict, we get milder seasons. And overall, this caused a cooling trend. All right. So why does it cause a cooling trend overall? Because glaciers will tend to grow when the summers aren't hot enough to melt the snow that fell in the wintertime. So overall, we get a cooling trend when we're on a total global scale, when our axis is tilted more vertical. Lastly, the more difficult one probably to understand is this idea of axial precession, the wobble of the Earth's axis. That cycles every 24,000 years, and it affects when in Earth's year the Earth is pointing towards the sun. Okay? So think about it this way. Right now, in January, we're closest to the sun, but what if we were in July closest to the sun? We'd experience even more significant seasons. So that's why the wobble influences the heating of the Earth. Perihelion means, para means around, helio means sun. So when we're closest to the sun, that occurs during the southern hemisphere summer, as we've just said, or our northern hemisphere's winter. Therefore, the southern hemisphere right now, they feel slightly more extreme seasons than we do in the northern hemisphere if all other factors are equal. So what does this mean in summary? Well, what this means is the previous ice ages were not due to carbon dioxide release. They were due to different amounts of energy that the Earth's rock was absorbing from the sun due to these changes in the orbital patterns. When all of those patterns together, called the Milankovitch cycles, are combined, we can accurately predict these ice ages that occurred over the last almost 1 million years. So to reiterate, the last ice ages were not, in fact, caused by increased carbon dioxide levels. So yes, we have had major changes in Earth's climate, but because we're accelerating carbon dioxide into the atmosphere, we're entering different kinds of territory. So let me explain this in a different way. The previous ice ages we had, the causation between carbon dioxide and temperature were actually the opposite. In fact, we had warming occurred first, and then carbon dioxide went up. Okay, so for example, if you look at this slide here, on this axis we have carbon dioxide through time. Here's today and here's in the past. And notice where we are at, way up here. We're almost 400 parts per million right now, well off this chart. These were previous temperatures. If you draw a line together, you'll see that in the previous cycles, temperature went up and then carbon dioxide went up. Well, why did that happen? Well, that's because oceans warmed, and as the oceans warmed, because they were getting more heat from the sun, they released the carbon dioxide that was dissolved in the ocean. More carbon dioxide in the atmosphere then increased the heating, and we get this positive increasing in heating. So carbon dioxide played a role in previous climate patterns, but it was not the cause. So what I would like to do now is show you a Jamboard that I think might help us understand these feedback systems. So during the development of ice ages, we get these triggers. This is part of a systems approach to understanding these cycles. So when we have warming trends or interglaciation periods, that was all through the Holocene. The last 15,000 years, we've been in this nice, moderate, warm environment. That's caused by these Milankovitch cycles. It's caused by our arrangement that the Earth is in relationship to the sun in its orbital patterns. So that caused increased heating, like Milankovitch explained. Increased heating started to warm up the oceans, and the oceans then released more of their carbon dioxide. We now know that carbon dioxide traps traps infrared heat better as a gas, and that increases heating, so we get this positive cycle developing. That led to a melting of the ice sheets, and when the ice sheets melt, because ice is very reflective, the Earth is actually, as a system, absorbing more heat. That then continues to accelerate this. Now, I have a picture of a glass here, which you can't maybe see very well. If you set a cup of water out overnight, and the next morning you look at it, you'll see all these air bubbles that form on the side of the glass. That's gas in the water escaping from the cold water as it warms up and going into the atmosphere. So our ocean is also fizzy. It has oxygen and carbon dioxide and other atmospheric gases dissolved in it. And as that ocean water warms up, that carbon dioxide more readily leaves it. So during the Ice Age Milankovitch cycles, this trigger event was influenced by CO2, but it was not caused by CO2. The main driver was the Milankovitch cycles. Now, if we think about it in the opposite sense, and if we compare what happened in a cooling phase, the Milankovitch cycles decreased heating. Decreased heating allowed the ocean to keep its CO2, so we had ocean absorbing CO2, not releasing it. That therefore decreased the temperature of the Earth even more and caused more decreased heating. This led to, these are supposed to be ice caps. These are continents. This is ocean. We get growing ice caps, which then reflect even more heat from the Earth, which then even decreases the temperature more, and we trigger an ice age event. That ice age event continues until over a 30,000 year history, etc. The Milankovitch cycles change again, and it shifts the whole system back to this warming trend. So this is what explains the previous ice ages, but now let's move to what explains the current anthropogenic climate change problem we have. We have to add a new element here. We have an industrial age where we're burning fossil fuels, increasing elevated CO2 as we've discussed, which then increases heating and ramps up this whole system. In fact, without the industrial age, we would be headed into a cooling trend with the Milankovitch cycles. We're supposed to be going in the next hundreds of years and into the next thousands of years. We should be heading into another ice age. So that's what this dotted line represents, but it's not happening. Climate change caused by humans is overriding the last cycle. In other words, we're not likely to head into another ice age. We're likely to head into a superheated circumstance where the Earth's climate will warm at an unprecedented rate. So if we go back to the presentation, I just want to end with kind of a sobering slide here. The last time the CO2 levels were this high was around 3 million years ago. So this graph takes a little bit of work to understand. We have multiple panels that look at changes in the carbon dioxide levels through time. And you'll notice if we looked at the Earth over 400 million years, there have been times where we've had much, much higher levels of CO2. And this has to do with the fact that the Earth's early atmosphere was largely carbon dioxide rich. It is life itself that changed carbon dioxide into oxygen and made our atmosphere more and more oxygen rich and less carbon dioxide rich. Volcanic activity, oceanic currents, and other things also changed carbon dioxide levels. So notice right now we have in the year 2020, we're down about 400 parts per million. Notice that 400 million years ago, it was 2,000 parts per million. Carbon dioxide levels were much, much higher. This is the age of massive changes of life patterns due to tectonic activity on the Earth. This is the age of the dinosaurs when we were producing a tremendous amount of plant material, large food reserves, lots of carbon dioxide in the atmosphere to fuel plant growth. And then that carbon dioxide level kept going down and down and down until the present. If we look at it in the terms of thousands of years, our carbon dioxide level used to be very, very low, and right now we're at an unprecedented increase. These 4 lines represent predictive models. If we don't control anthropogenic climate change, it is likely that we could follow trends that might mean that the amount of carbon dioxide in our atmosphere could rival what it's been hundreds of millions of years ago. We don't know. This is a topic for Monday's class. What I want to end with is just because carbon dioxide levels were higher in our past does not mean that it's okay. It is the rate of change that really dramatically disrupts ecosystems. And we'll talk about some of those causes in Monday's lecture when we look at the effects of climate change, carbon dioxide on ocean systems and ecological systems, and look at what our future trajectories might look like. Species, including humans, aren't able to evolve rapidly enough to keep up with this massive acceleration. So what I think is outstanding, sobering, is this panel shows for thousands of years we've had a very somewhat stable carbon dioxide level, even though we've been experiencing these periodic ice ages. Now we're on an exponential incline that rivals what the Earth has experienced over millions of years. So spend some time with the Milankovitch cycles and spend some time trying to understand these feedback systems between carbon dioxide and temperature as you prepare for the quiz on Friday.